This tutorial is to teach you how to work with a Quartus II Web Edition software. You'll be using that for homework for this fall 2016 semester for ELEC 1510 Logic Design. Over on the screen here, I've got a copy of your homework assignment up, and it starts off, it tells you your objective. What you'll do for the homework is you'll learn how to create a block schematic design, and then you will create a functional simulation of your design to make sure that your logic circuit works as expected, and then you'll create a timing simulation as well to learn about propagation delay in gates. You've been given some background material on FPGAs. So this semester, the Altera board we'll be working with has a chip on it that's called a field programmable gate array. It has several logic elements on it that you'll be programming. Right. When you create a design, eventually you'll end up programming the hardware board, this FPGA chip. We will talk about that in an upcoming tutorial. This background information is for you to read through. In your second assignment, you will learn to program the board, but for now today, we're just going to learn about the software. So we won't spend time on the board itself. Right. Since you'll be programming 3 gates, a NOT gate, an AND gate, and an OR gate, I've given you the truth tables as reference reminders. You, of course, are learning to use them. You'll very quickly learn to remember their behavior, but they're here for your reference as well. Right. The rest of the homework assignment talks about functional and timing simulation. Right. A functional simulation will show us that we're getting the results, the expected behavior out of our gate. A timing simulation, all right, scrolling down here, not very well. A timing simulation will show us the propagation of the delay of the gates. We'll come back to that when we get to that section. For now, I just like to start you in on the software. Right, so I've scrolled down to your cover sheet. This is what you'll be turning in with your homework. This sheet and the next page, right? You'll be putting your name on it, your grading summaries here, but what importantly, you need to follow these homework instructions. Right, so step A says if you don't know how to complete the steps below, and I wouldn't think most of you have ever used this software before, you were directed to come here to this tutorial. Right, so the first thing you're going to do is you need to create a project folder somewhere for this. Whenever you work with Quartus, it's very important that you put each project in its own individual folder. So if I actually then, I'm going to bring up my Windows Explorer here. Right, I'm going to, in this case, working off my home machine, I'm going to work off, let's see, I'm going to work off Dropbox because I can access Dropbox from anywhere. And so if I wanted to go to my folder for this fall, if I wanted to go into this class 1510, I might just go ahead and make a folder in here. You can right click to get new folder. You can choose it from the menu up here, or you can do a Control-Shift-N. So what if I just say this is LEC 1510 homework 4. Notice when I make a file name, I don't leave any spaces in it. This is very important. When you make a file folder, do not leave any spaces in it. Do not put any special characters in it other than this underscore. When you make a file folder name, you're better off to work in smaller case. You want everything to start with a letter of the alphabet. In this case, I started it with an E. So you can use any alphabetic characters in this. You can use an underscore. I did that to separate words to make it easier to read. You can use numbers. Just don't start the file name with a number. So follow a convention similar to this. All right, so I've created this file folder that we'll use later when we start our project. All right, and that's what we did from this instruction here. So start the Quartus II Web Edition. Oh, this should say 13.0, not 13.1. I'll make that correction right here. Haven't posted it on Canvas, so you will get the correct version. All right, so once again to reiterate, Quartus II Web Edition 13.0. Right, so if you're on your own computer where you've installed this, or on a lab computer, you want to go to the Windows Start menu. So if you're on a lab computer, you're working with Windows 7. On this particular computer, I've actually got Windows 8.1 installed. So I'm just going to bring up my search, which is showing on my screen 1. Let's see if I can get this to pop up over here. Sorry. So I'm going to pop over here where you can see it. So I'm going to type Quartus. And if there's more than one version that'll come up, notice I want 13.0. Service Pack 1 has the update I want. It's very important that you get version 13.0 Service Pack 1 for this design to work. Quartus is starting to open. Sorry, it actually just popped up on my other screen. So I will say new share. Actually, let me move it over for you. Oh, how nice. It appears to be frozen. I want to move it here for you. Let me close this down and let's restart and see if we can get it to pop up where you can see it, because I want you to see the full screen that pops up. So, Quartus 2, 13.0 Service Pack 1, still starting on my other screen, just not cooperating. All right, let me switch screens here. All right, so I've shifted over now so that you should be able to see this screen where Quartus popped up. You shouldn't have anything like this menu at the top. That's for our recording. But notice here, Quartus pops up, and I want to select on Create a New Project. That's the step we were doing. All right, New Project Wizard. We just don't pay attention to the screen. We just hit Next for introduction. And now this is very important. It asks what is the working directory for our project. By default, it tries to save it to where the software was installed. We don't want to put it there. We want to navigate to the folder we just made. So I'm going to hit these three dots for Browse. And then on my computer, I just put it here under Dropbox. And it was under Fall 2016, 1510. Here was my folder. I select that. And now it shows me the path to that folder. All right, notice I have no spaces or no special characters other than what Windows puts in this path. Name of the project. Well, let's just go ahead. I'm just going to call mine Homework 4. I could do the underscore. I'll just say Homework 04 right here. I'm just going to hit Next. Hit Next here. We have no files to add. Device settings. If we're programming the board, this becomes important. Right now, take the default so it doesn't auto-device. So I'll hit Next. And here, simulation. Choose Model Sim-Altera, and then choose Verilog. Eventually, we're going to learn to program in Verilog here, so I want you to work in an environment that supports Verilog. Get used to this step. All right, hit Next, and then we get to our last screen, which tells us where we're going to save our file, the name of our project, and our top-level design name. We'll talk more about that later. That automatically filled that in. We'll just click on Finish. And here we are now. All right, so what I may do is I'm going to move this to screen 2 so you don't get this other menu in the way. And I'm going to go back to where you can see that now. So new share, share screen. We should be back over to screen 2 now. Let me enlarge that for you. And you have an environment that looks like this. All right, so here in the Project Navigator window under Hierarchy, that we can see this is the chip that it just selected for us, the default. We won't worry about that, like I said, until we program the board. This is the name of our top-level design. We'll learn more about that later. I'm going to click on the Files tab, and notice we don't have any files in our project. What we need to do then is go to File, New, and whenever we draw something, we're going to use a block diagram schematic file. So block diagram schematic file, okay, and it pops up this area where we can start drawing our circuit. So the first circuit we're going to draw, if we go back here to our instructions, right, in step E, is we're going to draw an AND gate. Remember, an AND gate has two inputs, so we'll label our inputs A and B. Our output, instead of calling it F, I'm going to call it F AND. And we're calling our output G OR, so we know that's an OR gate. Later when we do H not, or H, we'll call it H not, so we know that's the output of our NOT gate. We'll see how that makes our simulation easier to follow later. But what we want to do let's go ahead and learn how to draw the circuit that is A ANDed with B, and our output is named F AND. So we have two inputs to this circuit, right? Here are two variables, A and B. Here are two literals, A and B. Let's see how we draw that. All right, so here in Quartus, right, we get this block with a default name. Let's go ahead and insert an AND gate. There's two ways to do it. You can go up here and you can click on Symbol Tool. So I'll click on that, and it opens another window where we can choose our symbol. Well, there's a lot of drop-down menus that we could go through to find this, but I know that this gate is named AND, and it's a 2 input. So if I type AND2 here in the name, it automatically goes to the 2 input AND gate. It shows me what it looks like. By default, repeat insert mode's on, so I could put multiple ones down if I wanted, but I'm just going to click on OK. And now notice as I drag my mouse around over here, I've got my AND gate. Right, so you can put it anywhere on your schematic. We can move things later. Notice it's ready to lay down another gate. I only need one, so if I hit the escape key, that goes away. So there is my AND gate. Now, we're also then going to need inputs and outputs, and we use input and output pins to do that. So go here to the pin tool, hover over that, and select input. And so I've got 1, 2. I've got 1 for A, 1 for B. Then I'm going to need an output here, so I'm going to go back to the pin tool, click on output, put that over here. Hit escape so I don't have multiple ones. All right, so whenever we work with these gates, these connections, our inputs will always be on the left-hand side of the symbol. The outputs will be on the right-hand side of the symbol. Now, I want to actually physically wire these together. There's a couple of ways I could do that. If you want to move anything, just click on it, hold down, move it around, drag it around. So I could, if I want to, take my arrow, place it over here, and when this becomes a crosshatch, I'm going to left-click and hold, and I'm going to drag the mouse over here to the start of this output gate, and I'm going to let go. I get this blue wire. If I hit escape, that's wired together. If I want to verify that, I can grab this with the mouse, so left-click, drag it, move it around, and notice my wires moving around here. So it is connected. So I need to connect my inputs as well. And so I could draw another wire from here. I could do this. And notice it's got kind of a bend. I could stop there. I can let go. I can go here. I can hover. I can hold down and move back to here and draw and make that connection. And I have that connection there. Another way I could do it is I can actually grab hold. So I'm going to left click, drag this over here, and just barely touch. Don't insert it all the way. Just barely touch that. I'm going to let go. And then when I drag this away, no, I didn't go far enough. See? Okay, just push that in a little bit, make the connection, let go. When I pull it out, that is also wired there as well. Right. Now, we need to give these pins some names, right? Our inputs are named A and B, our outputs named F. So there's a couple of ways we can do that. One way we can do it is I like to go up here and turn on the text tool. Right? And now, if I double click on that, right, or I highlight that in blue, I can just type A here, and it just writes over the top. By default, it said pin name 1. Now if I hit the enter key, it just goes to my next input, highlights that. So if I just type B, hit the enter key, I'm done. So we'll just go through my inputs. Right, if I have multiple outputs, I can select that. Once I highlight that, I'm going to type F and. Now, in the same way that we followed rules to name our file, right, we have to be aware of the fact that we can't leave spaces in these names here. So I can't leave a space between F and. I can use some underscores for special characters, but I'm going to make it all one word. You can use lowercase or uppercase for these names. Doesn't matter, just need to be consistent. All right, so now my output here is named FN. I'm going to turn off this text tool, because one other thing you should know is that you can draw anywhere on here. So with this text tool turned on, when I click with the mouse, I could just type some text. F, A, comma, B is equal to A and with B. And if I'm going to go back over here and click on the selection tool, so I turn that off. But now I've got this text comment. So this text comment doesn't affect the circuit in any way, but if I want to remind myself of what this Boolean equation is, I can put this here. Notice that might be a little hard to read. Let me use the zoom tool to make this a little bigger on the screen for you to see what that looks like. Now, I don't always like having these dots here in the background, so I will often go then to View, the View menu, and go down here to where it says Show Guidelines and turn that off. I prefer to look at it without these guidelines in the background. A little easier for me to read. But so now, like I said, this text is just like a comment here to let us know this output F is the result of A ended with B. You don't need to type that. What's going to happen is the fact that you've drawn this circuit element, connected it with inputs, and connected it to an output, you've just drawn your first logic circuit, and it will produce an output result for us. Okay, so let me just go back and turn on the selection tool again after I zoomed. And now you've got your first block schematic. So let's go back to the instructions. So we were supposed to draw a circuit to implement all of these expressions. Right. And the next thing you're supposed to do is, if we've drawn these, you're supposed to then create a functional simulation. Let me go ahead and show you then how to draw the other two, put them on the simulation, and look at all of our results. So now we need to draw, we need to have G OR as a result of A OR with B, and H naught is the output of A naught. So let's go ahead and create those circuits. All right, so that means I need a 2-input OR gate, and I can go back up to this logic symbol and click on that like we just did before. But now, see, it shows the last gate I used. I can type OR2, and then I've got a 2-input OR gate. So I'm just going to click on that. I'm going to put that down here. And now I need a NOT gate as well. So you can either then, like I said, we've just gone to the symbol tool. Another way we can do this is we can right-click on the schematic, and we can say Insert Symbol, and it brings up the same window. Now I need a NOT gate. If I type NOT, I get that, and I've got a NOT gate. All right. So now we have to add our other two outputs. So let's go back to the pin tool, output. Notice it's important that for output you use an output pin. All right, and I'm going to wire that. All right, so that's connected. Now, I'm going to wire this by hand, and I'm going to show you something that can cause you error. So crosshair there, hold the left mouse down, drag, and I'm going to drag this way into here. I'm going to hit escape, and notice when I went too far into this gate, I've got this big purple dot that stands for junction, and then I've got a tiny little wire with an X. That can actually cause some problems with your circuit. It won't generate an error message when we go to compile our design, but we want to make sure we don't have something like that. So it's a little bit hard at first to get used to where you should stop with your wiring. But I did this on purpose now to show you, if you have something like this, you need to get rid of it. So I'm just actually going to click on that little piece of wire. When you select something, notice it turns blue. I hit my delete key, that goes away. And so now I've gotten rid of that little bit of wiring. That extra wiring, think of it as maybe causing a short circuit, and your circuit won't perform correctly. All right, so we then said the output of our OR gate needs to be named GOR. Before we clicked on our text tool, and we were able to double click and change names. Well, you can actually double click here as well and highlight it without going to the text tool. And so that one we're going to name GOR. I hit the enter key, and this one we name H0. We go down here. All right, so now we've got all of our outputs named to match our circuit. Now, remember GOR was a function of A OR with B. I'm just going to turn the text tool back on and go down here and type this as a comment, that G is a function of inputs A and B is the result of A ORed with B. And then my text tool here, I'm just going to say H is a function of A is equal to A and apostrophe for A naught. All right, and then I'll turn off my text tool. Those are just, like I said, reminders to let us know what the circuit equation is. They're not required in order for the circuit to work. Right. Now, I don't need to draw two other input pins. As a matter of fact, if I were to put another input pin on here and label it A, I would get an error. What I can do is I can wire this to A. And I need to turn off my text tool. Right. Notice that's still highlighted, so let me go back to my selector. So I'm just going to bring this down here, crosshair here, hold, drag, and I'm going to go to A, and I clicked to get rid of the blue. So this little dot means that's a junction. That means this wire is now connected to A. So I've now effectively wired my input A to this AND gate and to this OR gate, right? And the same way, A should be an input to here. So I'm going to make that connection there. So now I've got A as an input to all three gates. And we also need to connect B to this OR gate. So crosshairs, hold, drag, connect to B. All right, that junction tells me that's connected to B. So now I've got the circuit fully drawn. All right, so what you want to do now is you want to save this. So go to File, choose Save. And don't keep the default name of block 1 that's up there. By default, notice this came up and named this homework 04. It always names it as the same as our top level design. And in this case, we want this to match our top level design name. So just go ahead and accept this default name. Notice the extension is .bdf. .bdf will be the file extension for all of your block diagram schematic files. So if you're ever just looking for a schematic file later that you need to open all by itself, you can double click on that. All right. It's very important that you save it in the folder name. So by default, it went to the file folder that we made, and we told it where to save everything, which folder to save everything. Because it's very important that you save everything within this file folder, this project environment, or later on you'll have problems. All right, so I'll hit save. And now, notice this file showed up as part of our project under files. That was empty before. All right, so here's the step we need to do to go ahead and create a functional simulation. We need to turn this design into some sort of computer code that this program can understand for the simulation. So we need to actually go here and double click on Analysis and Synthesis. Let's double click there. And it's going to go through and start compiling our design. And it came up and gave me an error message, which sometimes is not atypical of Quartus. So analysis and synthesis was not successful. 4 errors and 1 warning. You can never go on to your next step until you correct all errors. So let me click on OK. Notice errors always show up in red. So right here, this error, logic function of type OR2. An instance INST is already defined as a signal name or other logic function. So I'm going to double click on that. When I do double click on that, notice it took me to the schematic, because you're going to see later in the semester we might have multiple schematic files in here. So it takes me to the schematic where the error occurred, and it highlighted both of these gates. When we actually told it to put down the gates, it named everything, right? The name of the gate was AND2, this one was called OR2. Well, every single gate on here has something called an instance number. It's supposed to be a unique identifier. And Quartus happened to have a little bug in it here where it named this one INST and this one INST. That's what the error message is saying, is that we can't have 2 of them with an instance number of INST. So we just need to correct one, not both. We could double click on this, right? And I'm going to put a 01. So INST 01. Okay, now why did I choose 01? Well, this was named INST with no number. So I could have just put any number after that. Notice this one is INST3. I could have called this INST2. I just couldn't use this name or this name that's already in use. See how this is unique? This is unique, INST01, INST3. This is unique, right? Make sure there's no spaces or anything in there. And then we need to tell it to go back. So I'm going to double click on Analysis and Synthesis. It prompts me to save my file. Yes, I want to save my changes. And we'll let it go off and run. All right, now some of the warnings we're getting here are okay to get. You'll see as we work along, we'll actually get warnings occasionally. Later, we'll be concerned about some of the warnings, but right now I'm going to click on OK. And this one is OK, parallel compilation. So this in blue is a warning, is not licensed and has been disabled. Oh, this is because of the software we've downloaded and its license. It won't affect our design, create any problems. So we can ignore that warning and go ahead and create our functional simulation. Let me go back, and let's go back to the assignment. So we've done step B. We created our project folder. We started the software. We created a new project. We went ahead and completed step E. We drew a circuit schematic then to implement the following Boolean functions. Right. Step F asks us to create a simulation, a functional simulation. Right. And we want to show the results of all three gates. And you're going to end up printing it out. Let me scroll up here then to functional simulation. Right, so we use software, we use simulation to make sure that our designs are behaving or, quote, functioning as we expect. Right? Each one of our logic gates has unique behavior, and that's what we're going to do here with our simulation is we're going to show that the output of the gates matches our truth tables. Right here in this example, here's an AND gate. It has two inputs named A and B. Here are four possible combinations. Right? With two inputs, each input A can have a state of 0 or 1, B can have a state of 0 or 1. So the state is always binary, two possible states, 2 raised to the number of inputs, 2 squared, 4 unique combinations, 0, 0, 0, 1, 1, 0, 1, 1. So those are the 4 unique binary combinations we can have as inputs to our circuit, to our AND gate. Our output, as we know, anytime any one of the inputs to an AND gate is a 0, then our output will be 0. So X will be 0s in all three cases here. The only time the AND gate outputs a 1 is when all of the inputs, so 1 AND with 1, are 1s. And so what we do is when we run a functional simulation, we generate a waveform. We generate this vector waveform. And so when we generate the waveform, we generate it in a way that we actually then use each one of these input combinations, 0, 0, 0, 1, 1, 0, 1, 1. Let's take a look here. So here's an example of a functional simulation timing diagram. So over time, we'll assume that time starts on the left here at 0. And then when A is at a low level here, we consider that to be 0. So right here, A is a 0, B is a 0. And so A ANDed with B, or 0 ANDed with 0, gives us an output value X here of 0. Right? In this next time frame here, A is low, so 0. B is high, is 1. So that's 0 ANDed with 1. That's this entry of the truth table right here. 0 ANDed with 1. Still our output X is a 0. In the next time frame, B is 0, A is 1. That's for this particular combination. A is 1, B is 0. Notice our output X should be 0. It is, it's low here. Finally, in this time frame right here, then we see that A is 1, B is 1. 1 ANDed with 1 gives us an output of 1. And this timing simulation just went on and repeated the same thing over and over. So what we did here is we just checked each of the possible inputs. We checked the output to make sure the circuit was behaving as we expected. It did. So we know then, we'd say our simulation results gave us a successful result. We verified the behavior or the function of the circuit. Right? So let's go ahead now back to Quartus and create our own functional simulation. We'll go to File, choose New, and now we say University Program VWF. VWF stands for Vector Waveform. Click on OK. It's going to open up a new window here. Let me just minimize this. Right, we open up this new window, and let's go ahead and set our end time. So let's do Edit, set end time. It pops up a menu. We don't want microseconds. Our gates are going to work in terms of nanoseconds. So let's just choose 50 and change the US from microseconds to nanoseconds and say OK. And it changed then our length of our simulation that we're going to run. Right here, I want you to right click and say Insert Node or Bus. And then it brings up this window. Click on Node Finder. It brings up the Node Finder window. Sorry, it keeps popping these up on my other screen and I'm moving them over. So this says pins all. I'm going to click on list, and it's going to list all the input and output pins in our project. Well, we have A and B, FN, GR, H0. So we need to select the ones we want to be in our simulation. We want all of these to be in our simulation. So here under Nodes Found, If you use the double right arrow, it selects them all and moves them over to selected nodes, and just click on OK. So click on OK here. Notice the radix is binary. It's that by default. We want it to be that way because we're working in a binary system. So click on OK. And now all of these signals are added to your simulation. But by default, both of the inputs are shown as zeros all the way across the simulation. These cross hatches here show us that we haven't run the simulation. That means that we don't know what these outputs are for these particular inputs. But what we need to do next then is to set up our simulation, right? We want to set up our simulation in a way that we get all possible inputs for A and B. So we want the combination 0, 0, 0, 1, 1, 0, 1, 1. Well, let's notice then column B here. Notice then that oscillates from 0, 1 to 0, 1. This goes from 0 to 1 while A remains at 0. This then goes from 0 to 1 while A remains at 1. So this A is at a slower time period, slower frequency, right? Longer time period than this. So what we need to do is we're going to choose a time period. So I'm going to go back here to the simulation, go up here to the little stopwatch icon, which when you hover over it says Overwrite Clock. Sorry, but before I do that, I need to select one of these inputs. So I'm just going to click on B, left click, see how that turned to blue? Now I'm going up here to Overwrite Clock, clicking on that. It brings up a clock menu. Well, let's just use the default of 10 nanoseconds and click on OK. 50% duty cycle. And what that does is notice right here we're at 0 picoseconds. So between from here to here, 10 nanoseconds. 10 nanoseconds was our time period. In there we get one complete clock cycle, meaning, and we use the default 50% duty cycle, meaning for half of that period, or 5 nanoseconds, right, for half that period. So what I did was I right-clicked on this to move this over here. So from 0 to 5 nanoseconds, our signal was low. And I'll right-click on this again, the pointer. And then from 5 to 10, our signal was high. And notice this just oscillates between 0 and 1 all the way across here. Right. So now what I want to do is I want to click on A to select it. So it's highlighted in blue. I want to go back up to Overwrite Clock. And instead of using 10, I want to double the time period because A uses double the time period of B. So I'll just type 20. Click on OK. And so now I left click to bring this back. Notice A stays low at 0, 0, while B oscillates between 0 and 1. A goes high, while B oscillates between 0 and 1. And then this pattern just begins to repeat itself. So for our functional simulation, we'll be concerned about this first part of the pattern. Now, you get used to these timing diagrams or these vector waveforms of looking at them and knowing the zeros and ones, but I like to see them on the screen. So what I want you to do is I just left-clicked on that to select it. I'm going to then control left-click so that I now have selected both A and B. They're both highlighted in blue. Right-click your mouse and choose grouping, and then choose group. And it comes up and asks you to name the group. It really doesn't matter what you name it. I'll call it input. Click on OK. And now notice what it did was it took the A and B signals. So the rightmost bit here is B. A is the top bit. So I'm going to click on this little triangle to open it. So by default, whatever signal's first in this list is first in this list here of binary numbers. So it's the most significant bit or the leftmost bit. This signal is the next bit. In this case, the least significant bit. And I think it makes it easier to read your input if we do this. If we can see that now we've got our 0, 0, our 0, 1, our 1, 0, and our 1, 1. Like I said, it just repeats over and over again. So let's go ahead and save this. So File, Save. And it's important we save this in our project folder. It gives us a default name of waveform. I'm just going to call this Fun Sim for functional simulation. Click Save. And now we're ready to run our simulation. So we saved that. But now to run our simulation, go to the Simulation menu, click on Run Functional Simulation. And it'll pop up a window, something like this. and it's issuing some commands, it's creating the simulation. So if we've done everything correctly, we should get an output and no error messages. Right. So I'm just going to blow this up, maximize it, and here's our output then. So it ran the simulation, and now I can take a look at. So when our inputs A and B are 0, 0, let's look at AND. Right. Our output AND, we said we know from the truth table that when any of the inputs to the AND gates are zeros, our output should be a 0. So sure enough, in this time period, F AND output is a 0, it's low. It's a 0 here, it's low. It's a 0 here, it's low. But notice then when both of our inputs are 1s, then our output is also a 1. And then it just starts over again, so we can just ignore the rest of the simulation, right? We could go back and set the end time to 20 nanoseconds if we just wanted to see one complete cycle of this truth table input. Right, so now we verified that our circuit, our AND gate works or functions as we expected. Let's take a look at the OR. Now, so for the OR, remember for an OR gate, if any one of the inputs are 1s, the output's a 1. The only time you get a 0 output out of the OR gate is when both inputs are 0s. So right here, both A and B, so here, this is the result of A ORed with B. Notice that's a 0. But now here, this is the result of A ORed with B, or 0 ORed with 1. So our output is a 1. This is the result of 1 ORed with 0, output is a 1. And this is the result of 1 ORed with 1, our output is a 1. So our circuit is working as we expected for the OR gate. Finally now, if we go ahead and take a look at H0. So I clicked on that to highlight it. Remember, H0, our output is simply the A gate, inverted A0. So let's look here. As long as A is low, A0, the complement should be 1. So as long as this is low, zeros, the output is high. And as long as the output here is high, I'm sorry, the input of A is high, here and here, our output is low or inverted. So the NOT gate circuit is functioning as we behave. So like I said, the purpose of the functional simulation is to make sure that our circuit is working as expected. We use software, simulator software, to do that because as you can imagine, as we get more and more complex circuits, we don't always program them straight to hardware, where we look at the functional simulation first to make sure they're working as we expect. All right. Oh, I'm going to then, part of your assignment says you should print this. I'm just going to go ahead and close the window here. Right? You should print yours as you're watching along, working with this. All right, so let's go back. We're about done with the assignment. The next thing we want to do is a timing simulation. So what I should point out to you, I shouldn't have closed that, should I? Right? Let me just rerun it. So the way I ran it before with simulation, run functional simulation. There's also an icon here that does the same thing. Let me run that again. So I want to point out something on the transition. All right. So what I want to point out on the transition, what a functional simulation does, is notice then right here, at this particular time, let me, at 10 nanoseconds, when our input signal A changed from 0 to 1, it did so instantaneously in that moment of time. At the very same time, our NOT gate output also changed. So in a functional simulation, we don't take into account any sort of gate delay. And in real world devices, right, according to the physics, things don't change instantaneously. Gates take a little bit of time, and we call that a propagation delay when they take a little bit of time. Let me close that down. So here, this in your homework talks about propagation delays. These devices have, they're usually in terms of nanoseconds, but will take a little bit of time in order for your circuit to change. Right. So in this example, this one shows then that as this gate output was changing here, B had a signal change from here to here, but the output F took just a little bit of time for it to rise, so we call this a rise time propagation delay, to rise from 0 to 1, from low to high. Over here, when there was a change, when both of these went to 0, so this was an AND gate, so both of these inputs were 1s, and so we needed to transition to an output of 1, but it took some time. That's our rise time propagation delay. Over here, when both signals transitioned to low, it took a little bit of time for the signal to fall from high, a 1, logic 1, to low, a logic 0. So we call that a fall time propagation delay. Right? And they're not always the same in gates. So they're usually pretty close to one another, but they're not always exactly the same, really because of the way the device was manufactured. Most of the time when we think about gate delay, we'll talk in terms of an average delay. So an average propagation delay, if we measured both of these, the rise time and the fall time delay. So if we measured both of those, sum them and divided by 2, we would get an average delay for the gate. Right, so you're going to do that then in your homework. So I'll show you now how to create the timing simulation. We completed step F. We've gone to step G in your homework now. Timing simulation. We go back to the simulator, go back to this, and we can't run a timing simulation if we've not fully compiled our design. Let me go back to our circuit schematic here. So back here, remember we did a double click on the analysis and synthesis? That works for a functional simulation. If you want a timing simulation, you must do a full compilation of your design. And what we need to do is we need to go here to the Start Compilation icon, click on that, and then go ahead and fully compile our design. We could have done that in the beginning, would have saved us some time knowing we wanted to do a timing simulation, but I wanted to show you how to do the analysis and synthesis step as well as the Start Compilation. And compilation, as you can see, is going to take a little bit more time. So if you're just doing a functional simulation, I would just do the analysis and synthesis step to save myself some time. We're also going to see that we're going to generate some more warnings with this one. It won't be anything we need to concern ourselves about, but now we've got 12 warnings. Before we had 1, sorry. Click on OK. If you want to see a list of all the warnings, you can click there where they're highlighted in blue. So once again, parallel compilation is not licensed is fine. Logic lock, that warning's fine. The fact that we don't have incomplete I/O assignments right now, that doesn't hurt. We're not programming a board. No clocks, well, no, we're not using a clock. But we can ignore all of these. Right. All right, now let's take a look here. Notice logic elements. Right, this particular chip it selected, it auto-selected this particular chip would have 14,400 logic elements on it. As you can see, us using a few gates does not use very much of the chip's capacity. We won't come close to using the chip's capacity in here this semester. All right, total pins. So that measures the input and output pins. We have 2 input pins, A and B, and we have 3 output pins, F, G, and H. Right? All right, so let's go back then. I left the simulation screen up the waveform. We're going to use the same waveform that we used before. Let me minimize some of this in the background to make this easier to read. Right, now that we recompiled, we're just actually going to tell this to run a timing simulation. So let's just click on that. It's going to bring up this window again as it reruns. And wait, no errors, good. And it pops up, sorry, it keeps popping up things on my other screen. Ignore the barking dogs in the background, sorry about that. All right, let's take a look now at our timing. Here is our output. So we see these crosshatches right here. And that means that up until this point in time, because of gate delays, we didn't know what the output was on our circuit. So what we're going to do now is let's take a look at the not gate propagation delay. So right here. Now let's ignore so if I go to the beginning here, so if I go here and I right click on this, notice it takes me to the first instance in time where it knew what the output was, about 5.87 or 879 seconds. I want to take a look at the falling edge and rising edge delay. Let's go over here to where we had a falling edge. What would have caused this in our particular output? Well, remember that the output of this circuit is A naught. So let's go to right here. So this point in time right here. No, sorry, let me go right here. So actually I don't need to go. So you can see at 10 nanoseconds without even putting the cursor there. There it snapped to the grid. At 10 nanoseconds, A went from low to high. So it went from 0 to 1. So when this goes to 1, we would expect the output of our gate to become a 0. But it didn't become a 0 until this particular time right here. So if I click on that, right, we see that at 16.281 nanoseconds, the output of our NOT gate transitioned from high to low. So the input transition was here at 10, then the fall time delay, so fall time because the output signal is falling from high to low. The fall time delay then is this time, 16.281 minus the 10 nanoseconds, and you'd see then that our fall time delay of this gate is 6.281 nanoseconds, which then in your homework, you would go ahead and record that right here as the falling edge delay, 6.821 seconds. Now, don't record that in your homework, right? You're running your own timing simulation, and you may get a different result on your software. If you do, don't be concerned about that. It should be in terms of nanoseconds, but it might be slightly different. It might be slightly different on everything that everyone turns in because this is a software simulation and not necessarily based on a real chip. So sometimes they do vary from student assignment to student assignment. Right? Like I said, you would record your falling edge delay right here of your 6.281 nanoseconds. Right. Now let's look at the rising edge delay for this NOT gate. So we can see that the gate transitions back from a 0 or 1, the edge rises from low to high right here. So we know then that we look for where does this transition from high to low? Well, it transitions here at 20 nanoseconds. A goes from 1 to 0, high to low here. We know that when A is a 0, the output of the NOT gate should be a 1, the inversion. That doesn't change till over here. So our start time is 20 nanoseconds. Right, if I double click till we get there, our end time is 26.5. So 26.57 minus 20 gives us 6.5 nanoseconds then for our delay, our rise time delay, which you would put rising edge delay in your table right here. Don't forget to record your units of nanoseconds. Whenever you write anything down, make sure you're saying what your units are, nanoseconds. And then you can calculate your average delay by adding the two together and dividing by 2 and filling in your table here. All right. So that's our timing delay for the NOT gate. So if you want to find out what it is for the AND gate, well, let's look at our first rising edge output on the AND gate. So remember F right here. So remember F then is the output of the AND gate, F AND, and that's why I had you name these. Instead of F, G, and H, F AND to remind you that this is the AND gate, G OR to remind you this is the OR gate, H NOT, the NOT gate. All right, so back to the AND gate and its propagation delay. It rose from low to high at 21.916 nanoseconds. Let's see where the input transition. We know that the input transition that would cause this from to go to low to high should be when both of our inputs are at 1. So right here, at this particular time, at 15 nanoseconds, our input B, A was already a 1, B transitioned from 0 to 1. So right here at 15 nanoseconds was the time that both of our inputs were 1. But notice it took until 21.916, so 21.916 minus 15 would tell you that your rising edge propagation delay on your AND gate is 6.916 nanoseconds. Right? If you want to find your falling edge delay on your AND gate, well, let's go over here. So the output of the AND gate fell from high to low, from 1 to 0 at 27.20. What triggered that was right here, after both of these inputs were 1s, when they transitioned, so at 20 nanoseconds, when our inputs transitioned to 0s, remember 0 and it was 0, should give us a 0 on the output. So right here, we can see that our falling edge is 27.201 minus 20, or 7.208 nanoseconds. So you'd record both of those numbers in your table, right? And then you're going to do the same thing to find your rising and falling edge delay on your OR gate. So now you have an idea of how to find these in your timing simulation. And you'll be printing this out and turning it in as well for your homework. Right, so you fill in your table, do your calculation, you print out your results, staple these to your cover sheet, and your homework is done. So that is your tutorial then on how to use Quartus to create your first schematic and run your first simulation. I'm going to close this. I'm going to go back to Quartus. I'm going to close the waveform back here. Let me bring up Quartus and say a couple more things. So notice that waveform we saved as part of our project. If you need to rerun the simulation later, you don't have to recreate the waveform. You can just double click to open it up, and then you can choose either one of these buttons to run your simulation. Now, if you ever make any changes in your design, right? If you go back here and make some changes in your schematic for some reason, then you would have to go ahead and recompile your design before going back and rerunning your simulation. But for now, that's all you need to do with your Quartus project. I'm just going to go ahead once again and close this simulation window, and I'm going to completely shut down the software to do that. Well, there's a couple ways. Let me just go ahead and say File, Close Project, and notice that absolutely closes my project. If later you need to come back and reopen your project, well, if you started the Quartus software, you would just go to File, Open Project, and then navigate to wherever your project is. It went straight back to that folder for me since I'm still in that environment. And you would look for this file, homework04.qpf. So that extension .qpf stands for Quartus Project File. QPF, Quartus Project File. And if I click then on that on Open, well, it doesn't open my files, it opens my project environment. If I want to see the files, I just double click to open them, right? So that's how you can get back into your files if you need to recreate something or make any changes. Print that out. And the other thing you were instructed to do is to print out your circuit schematic and put it on the document. Make sure you print it in a way that's viewable. So you can do that by going to the file print, or you can use a print screen of it, whatever you need to do to print it out. Don't forget to put that with your homework. All right, so that is actually then the end of this tutorial.